How's everybody doing today? My name is Gene Beebe. I'm the area sales manager for Vector. I've been fortunate enough to know Tom since about 2007 with Kurz. Tom has spent a few years with Kurz. He told me right before we got on here, he is just shy of 40 years. So if anybody knows thermal dispersion flow meters in and around combustion air and difficult applications, it's Tom. Recently, he was the international sales manager for Kurz. I've done many projects overseas and has supported us very, very well here in the States as well. So Tom has an interesting product that he wants to present to us today. It has solved several problems that we've had along here in the Gulf Coast with our high humidity applications in combustion air. And it's very much a newer technology in a product line that hasn't had a lot of evolution into that. So I'm going to turn it over to Tom and let him go, and we'll answer any questions when we get done. Thank you, Tom.
Hi, everybody. Thank you. Hope you can hear me okay. Just wanted today go over a little bit about our wet gas flow meter and why we did it, and maybe some of the newer applications we're starting to solve with it. But basically, this whole idea started with some issues we were seeing in the municipal side of the business, in digesters and landfill gas. And one of the things we noticed in these applications was that the measurement of the totalized measurement of all the digesters was usually different than the combined flow measurement after a gas conditioning system, where they removed the volatile organic compounds and the moisture and then ran that gas into maybe a cogeneration plant and make a little bit of power. So because of this, our product manager, business development guy, and our engineering manager started working very hard on the digester gas applications to figure out what the problem was. And basically what we found was that all thermal mass meters were over-reporting the true flow rate in these wet gas applications. And out of just some interest in performance, the engineering manager started increasing the differential temperature at the tip of the probe. So instead of a 75 degrees Celsius sensor overheat, we started running it a little bit hotter, 100 C, 200 C. And what we found is as we increased the temperature of the sensor, the over-reporting was reduced proportionally. And currently, the standard wet gas flow meter actually has a sensor overheat of about 300 degrees C. And because of this, we're able to actually reject the water in the process. And this is what we first saw in the digester applications, was trending for, say, a full day on what the flow meters were reading. And you can see here that the treated gas without any moisture in it is running about 100 SCFM. And then the standard Kurz meter and the wet gas meter are over-reporting that reading a little bit. Now, I want you to remember that we are a wet device, and so we are measuring the combined moisture and gas in the process. So that 110 reading, whatever you see, is not actually a 100% over-report. Some of that is due to the moisture that we're reporting in the process. So we're giving you the wet standard cubic feet per minute. We have included in our flow meter for these applications that are saturated, we have included a dry gas calculation built into the flow meter. Since we know the temperature and we know that it's saturated, we can actually calculate the moisture. And in these saturated applications, we can give you the dry SCFM or the wet SCFM. You'll see the yellow line there is actually the constant power type anemometers. So at higher flow rates, they actually cool down to a much lower temperature. And you can see they're subject to a lot higher over-reporting. But in the middle of the day, when you have the hottest part of the day, beating on those pipes, keeping those pipes hot, and you have very little water condensation in the pipe, you'll see we all read better under those drier conditions. And Kerr's has always had a better performance than most companies because of our sensor overheat. That 75C overheat puts us at almost the boiling point of water, even for our standard meter design. Okay. Now the sensor itself is just two RTDs. PT100 style RTDs. We use a platinum wire wound RTD. The shorter element is the reference temperature sensor, so it's 100% passive RTD, and we use that in the control to drive the heated element. The longer sensor is we add power to that sensor to maintain a constant differential temperature at all flow rates. Okay, so this is a constant temperature design. The real difference between the wet gas meter and the dry gas meter is that we drive the wet gas meter with a much hotter delta T, and we've separated those two RTDs compared to our standard sensor design. So those two RTDs have about a 1/4 inch spacing between them, so that we don't allow, depending on the mounting of the sensor, we're trying not to allow any water to drip or bridge those two RTDs, which could be a source of error or a source of spiking on the output. Okay. Now, out of curiosity, I thought you might want to see what the raw sensor signal is actually doing. And one of the advantages of this type of device is you see we have an active 0. So 0 is a data point for us, regardless of which design you want to use. Because we're heating that sensor to 100 degrees or 300 degrees in some cases above the process temperature, it takes a certain amount of power to run the sensor even at 0 flow. So 0 is a data point in the calibration. You'll see 0 watts on all your calibration certificates. You can verify the meter's integrity even with no flow in the line by looking at, say, the 0 flow power and the temperature. You can make some first order assumptions about the health of the device. And you'll see on the right hand side there the wet gas meter design where we've increased the power. So you see that we use over 2 watts of power at 0 flow instead of having to get to almost 6,000 feet a minute to get to an equivalent wattage on a normal flow meter. But because we're working at such a higher wattage condition, we actually have a much steeper output. So this thing is proving to have an incredible signal to noise ratio and incredible repeatability at these very low velocities. And I am at the point now where I recommend the wet gas flow meter for all low temperature applications that are also low flow, just because even if it's not wet, you get a much better signal output, which translates back to better signal stability and lower noise on the output. Now, why it works is I was staying up late one night and I accidentally saw a Mythbusters episode on Leidenfrost Effect, and it made me realize that is why that is one of the reasons at least we're able to reject the effects of the moisture in the line. When you have a surface that is about twice the boiling point of the liquid, it is very hard for that liquid to actually touch that surface. And you see that when you're cooking, when your wife's cooking and she maybe throws a little bit of water in the frying pan, and as soon as those droplets coalesce, in fact, they're no longer touching the hot surface. There is about a 0.2 millimeter vapor barrier between the water droplet and the hot surface. So I use this to explain that we're not actually just boiling off and flashing off the water. We are in fact repelling that water from touching the sensor itself. Here we have a small presentation, wet gas simulator that shows several different designs of flow meters and how they're affected. So let me just describe what's going on here. You can find this wet gas test on YouTube, by the way, if you want to see it again. But what we have here is a wet gas simulator stand where we have 3 flow meters, and we have, let me stop this for a moment. We've actually set these flow meters up to mimic the performance of several types of flow meters. One has a 10-degree overheat, only 10 degrees Celsius overheat. So this thing's only running about 20 degrees Fahrenheit above the process temperature. This flow meter is going to be at the 55 degrees C overheat, which was our standard before, and we've now increased our standard to about 75 degrees C overheat. And then this one will be the 300 degrees C overheat sensor. And we have a small supply fan here, and we have an inlet flow meter here as the reference dry gas measurement. Here I have a small tank of water and a little disco fogging device here that'll throw a lot of water in the air, trying to simulate condensation in the line. Let's see how this proceeds. You'll see here now that as we start running the flow, and as long as we don't have this water in the process, somebody's going to turn the flow on. You'll see here that under laboratory conditions, under dry laboratory conditions, we all perform about the same. Okay, the 10-degree overheat is reading 70 something, and the 300-degree overheat meter is reading 70 something. So we all appear to operate similarly in a dry environment, laboratory environment. The problem comes when you have dirt or moisture in the line, and that's where these 3 devices will perform quite differently. So as we throw a little bit of water in the process, you can see now that the wet gas flow meter is only reading about 5 SCFM over the dry gas flow measurement. And again, we're adding moisture in this box. So this is not a 5 SCFM air. We're actually measuring the combined water vapor and dry gas flow in the pipe. But you'll see here that the lower delta T flow meters, the 50 degree and the 10 degree overheat, they tend to over-report the flow considerably. In the municipal business, we had a lot of customers complain because they had used low-quality competitive flow meters to calculate their digester performance, and they actually bought cogeneration plants that were later on found to be oversized because they did not have the amount of gas that they had thought they had in the process. So that was 3 KERS flow meters that were set up quite differently, and in this demonstration video we're actually using the competitors' flow meters. We've blocked them out just so you can't tell who's whose, but this shows 4 different competitive undisclosed brand flow meters and how they perform. Anybody wants to see this wet stand in action, Gene Beebe has one in his office there in LaPorte. We built about 4 of these for shipment around the world for trade show and training purposes. Now we're going to show the 4 different actual competitive flow meters. I'm sorry, there is a normal audio on these videos, and unfortunately I'm having trouble with my computer audio, so I'm called in through a phone line here. But you can see here with this brand D, as soon as they turn that water on, it starts to over-report. And what we found is that with the brands that had the lowest overheat, they had the worst over-reporting and stability problems. And the blue one is, of course, the KERS wet gas meter here. so we know its performance based on the past video. So once we got done with this testing that we did on all the digesters and landfills, and we were pretty well established in the wastewater treatment plant side of the business, the CEO, Mr. Dan Kurz, asked me to start looking for wet gas applications in heavy industrial environments. And that's when I started thinking about some of the problems I'd had in the past with moisture on ambient air inlets, as well as with dirt contaminants on ambient air inlets. I had several refineries complaining about these air inlet applications where they would have to clean the sensors quite often, and they also were giving them noisy results in rainy events. And so here's three different ducts that would be typical of a wet gas installation now. This particular duct here on the left is in Texas, and it has currently 2 wet gas flow meters in. They're used for oxygen set point control. This is another refinery, I believe is over in Louisiana area, and this is actually a refinery overseas, and they just bought the K-bar flow meter that's going to go into this stack. And that refinery has used Kurz for many, many years, and they're hoping to get better performance out of the wet gas meter. Another refinery over in Europe now is going to be installing a bunch of Kurz in these analyzer vent inlets. So these are environmental monitoring facility within the refinery, and they have to bring air into this facility and analyze it for pollutants. So they have about 7 different ducts they're going to measure with single point 454s, and then those readings all go back to this instrument control room. So. Now, one of the problems with the air inlets is that at very high vacuum conditions, you can actually induce fog. It's vacuum-induced fogging, so that even though it may not be wet outside, you're actually getting a more moist fluid inside that duct. So that additional moisture or fogging is problematic in that it causes the meter to over-report, maybe to be a little bit noisy, but it may also cause any contaminants that are in the fluid to be a little bit more sticky in the process. So the first place I tried was on some wet scrubber stacks, and then most recently we've been putting these wet gas flow meter in on these ambient air combustion air inlets with very, very good success. So this is a facility in Texas, refinery there, and you can see here, this is before we put in the second wet gas flow meter. This particular application had been using Kurz for many, many years, but they'd been using the standard Kurz flow meter. And I went and visited them about 2 years ago, and they were discussing problems with signal stability and during hurricanes in particular, as well as dirt accumulation and having to clean the sensors quite regularly. And so I proposed the idea of testing a wet gas flow meter on that air inlet to see if it would improve the performance under wet conditions, as well as improve the performance for dirt contamination. And you can see here when, currently, by the way, they have 2 wet gas flow meters in this application. This particular graph is when we had 1 wet flow meter and 1 standard flow meter installed. And you can see here in the beginning of the day, we had fairly equivalent readings on the 2 meters. This is under dry conditions. And then we checked the weather, and we had rain throughout the day at this time period. And you can see here when the rain was getting sucked into that duct, my standard flow meter, while it was fairly good performance, it was a little bit noisier than my wet gas flow meter. So my wet gas flow meter here, you can see, is rock solid, even under those wet environments. And most recently, I called them to talk to them about the dirt accumulation or cleaning problems they had in the past. and their response was that they have seen no indication of any drift on this flow meter since installation. It's been installed now, I believe, just past 1 year, and they've never removed this thing for cleaning. So while I don't have any photographic evidence of it remaining clean, the customer feedback and indication is that there is no contamination problem affecting the reading on these flow meters. So I believe that the higher temperature flow meter is also keeping the dirt accumulation dry, so this dirt won't be sticky. It will dry out and carry on down the line. And the other issue is that we have such a large signal using this wet gas design with a higher wattage on the sensor that I believe that if you had a 1 mil coating of, say, dust on the sensor, it's going to have a lot lower effect on the sensor than, say, a 1 mil coating on a sensor that might only have a 10-degree overheat or a 50-degree Fahrenheit overheat. So KERS does use more power in their sensor than any other thermal mass flow meter in the industry.
So Tom, I want to add real quick, we're getting close on time. That particular customer was going to spend a lot of money trying to re-engineer that tower and put in larger baffles and more structure around there to try to keep the water out of the system. By switching over the KERS meter, it saved them a lot of time and a lot of money, and got a better response throughout. So they were very
lower maintenance. I think the maintenance guys are very happy at this point. So hopefully one of these days we'll be able to remove a probe and take a photo, but I think we're going to find it's quite clean. So, other applications I've been running into for wet gas meters is in the steel mill industry. I've found a bunch of wet scrubber applications. Again, I'm the international guy, so I'm thinking of some projects overseas. But we have some wet scrubber stacks on some sintering plants, as well as the blast furnace gas exhaust that I've just delivered a flow meter for that'll be installed this year. So hopefully we'll have some better experience on a blast furnace wet scrubber exhaust by next summer. So, but another interesting application is the steam condenser in a power plant. As a steam condenser has a vacuum exhauster pump on it in order to remove all the non-condensable gases. So they're cooling the steam down, they're condensing it back into water, and they're trying to remove any methanes or air out of that system, because air is an impurity in that system. Well, that is a very high vacuum system, minus 700 millimeters Hg, is a very low flow rate, because in fact they want zero flow in this process. So what they're really trying to measure is their air in leakage into their condenser. So this flow meter has recently been put online and is operating very, very well in this environment. In these applications, we tend to have a lot of straight pipe runs because this condenser is routed to the outside of the plant. But here's another excellent application in the power industry for a wet gas flow meter. You'll notice the sensor, when possible, should be installed from the bottom, usually a 4 o'clock position. This allows any water droplets that hit on the probe to actually condense maybe and drip away from the sensor. You could put it at 6 o'clock in this duct, but then I would be the drain plug when we pulled that probe out. So we prefer a 4 o'clock or an 8 o'clock position when possible on these wet gas applications. Obviously on vertical stacks, that's not possible, but we're still seeing very, very good performance. And flare gas in the oil and gas industry is very dirty. It's oily, it's wet. And so plus a lot of the ultrasonic meters are having trouble getting the very, very low flow performance. These particular photos are for Saudi Aramco, because again, I'm showing my my overseas side of my business. But you can see here on the left side where they've abandoned the GE Panametrics ultrasonic flow meters because they couldn't get the very, very low flow rates they were hoping to get. And and they're replacing them with the KERS flow meter. And even for in the oil and gas exploration now, for the oil exploration guys in Texas now, they've started to convert over from the competitors' flow meters or our standard flow meter to our new wet gas flow meter. And this is going to give them a lot better signal in these dirty, oily, wet environments. So anyway, the KERS flow meter has a lot of advantages for these types of applications. Of course, ease of installation and low maintenance and very, very high reliability are among many of the reasons we think we're a good option for these types of applications. If you're interested, there is another video on Leidenfrost Effect. You want to run that, Gene, or not?
No, I think we can start moving on. I had a question for you. I know that you mentioned that we are using a constant temperature style thermal dispersion. Now, there's several other manufacturers out there that either mimic that style or maybe go to a constant power. Could you spend just a minute or two on why KERS uses that constant temperature and what maybe the advantages are to that?
Well, the advantage of the constant temperature is primarily speed of response. Okay, if you're maintaining the same temperature at the tip of the probe, as the gas flow changes across the probe, you're simply cooling the surface of the sensor. So constant temperature is always important for control applications where you're trying to do maybe a fuel air feedback control. Constant power design anemometers use a fixed wattage on the sensor, and as you change the flow rate, that sensor has to heat up or cool down, sometimes a significant amount. So constant power type thermal anemometers, their response times are typically in minutes, whereas constant temperature thermal anemometers, the response times are in seconds. So constant power anemometers are typically only used in monitoring applications for maybe stack flow where you're not using it for control, or they use a lot of them in flow switch applications where they just want to know level in a tank and things like that.
Okay. Also, how do you make sure that the units are working fine? I mean, how do you calibrate it? How do you test it or verify that the units are working properly?
Well, first of all, a KERS meter has a lot of internal diagnostics already built in. We're looking at about 30 different variables within the sensor continuously, from dielectric strength to the ratio of the two RTD resistances and various other things that are being monitored. And if our internal diagnostics detect anything that we suspect may affect the reading on the meter, then the meter will automatically turn itself off and go into NE43 alarm mode to tell you that we suspect we have bad readings. If the KERS meter has no error codes, then it's going to be giving you a reading. For customers to validate the integrity of the meter, one of the things I recommend is, first of all, again, 0 is an active data point for a KERS thermal mass flow meter. So what I usually tell my customers is check the temperature reading on the device, because we are measuring flow and temperature. If the temperature is reading right, that's one variable that's positive. Check the power under 0 flow conditions. So if you can shut the flow off in the process, you can verify the 0 reading to our data sheet. And if the sensor is clean and reading 0 properly and reading temperature properly, you can pretty much make some assumptions that you're getting a good indication of flow. The only other thing you can do in the field is you can also calibrate the analog side of the electronics. So you can do a input or output calibration on the 4 to 20 milliamp outputs, just to make sure that the analog portion of that circuit is also working properly.
Good deal. I know that we have a couple of portables in our staff. Customers have portables as well, and we have been known to go out and do cross-stack testing. If you're interested in looking at a new KERS application and you have a port that's available, we could do some testing prior to that to see how the responsiveness is. I have to tell you, we have had very good success with KERS, and I'm very confident in the work that they've done and the work that Tom has done and support we get from KERS. Even though they're in California, they do work well in Texas. So we appreciate that from Tom. Nikki, I think we have time for a question or two.
We do have time. The first question would be, is the higher sensor temperature safe for use in hazardous environments?
Okay, absolutely. In fact, this is really the same circuit as our standard sensor. We're simply just operating it a little differently. So for explosive environments, we have a power limit on our probe of about 12 watts. So we only allow up to 12 watts of power. And so for explosive atmospheres or environments, for say Division I applications, the assumption is that the meter has failed and is giving full power onto the sensor. So the auditing agencies don't give you any credit for your smart electronics that'll shut itself down during these fault events. So what they want to know is what is the maximum sensor temperature that sensor can reach under a fail condition. So we did a bunch of diethyl ether testing where we elevated the temperature of the gas, and we actually induced a worst case failure into the sensor where we had full power onto the sensor. And what we found is that for ignition reasons, the effective sensor temperature is only about 90 degrees C over the process temperature. So even though we have maybe a 300 degrees C overheat on our sensor tip itself, it's a very, very small surface area. So it sort of comes under the intrinsic safety guidelines where you can have a spark even on an intrinsically safe loop, but that spark has so little energy, is not enough energy to cause ignition. So the same is true here in that the normal sensor and the wet gas sensor, in fact, are one and the same in this failed condition where you have maximum power on the probe. So if you read our safety approval, you will find that it has a 90 degrees C delta T. So there have been a few applications I've run into where there are special heavy gases that have very, very low auto ignition temperatures, and these are probably not for KERS. But for most of the applications for methane gas, hydrogen gas, the auto ignition temperatures are well over 1,000 degrees on those gases. So even with a 300 C overheat or even in a fail condition, we don't reach an ignitable point on our sensors.
Thank you very much. That's always a common discussion. They hear thermal and they just assume that it is an ignition source. Thank you, ma'am.
I've been getting that question for 40 years. So even when the sensor was only a 30 or 40 or 50 degree overheat, there was always that concern, but we do have safety limiting on the device.
Well, thank you very much, Tom, for your time. We appreciate it. We hope it was a very informative to those who attended today. If you have any questions, please reach out to us here at Vector, and we'd be more than happy to look at your applications. As soon as we're able to travel more, we'll be happy to bring Tom by and introduce him to you as well. So, Tom, thank you again for your time, and we'll talk again soon.
All right. Thank everybody else for attending. Thank you very much.